Okay, so let's see these examples that they're doing in the textbook. We're actually going back to the actual examples that they're using. And when you read this, you're going to be like, why did they choose it? Well, that's why I did the previous problems with you, is to help you mentally through this. So let's look at this. Example 7. It says, find the area of the region bounded by the graph of f of x equals x cubed, the x-axis, and the vertical lines x equals 0 and x equals 1. Well, we want to find the exact area, not the estimated area. So let's think about this. 1, what's the number of rectangles? So n is the number of rectangles. We no longer get to put in something like 5, right? Step 2, let's think about the width. What's the width of each one of these? What would the width be? Well, the width is delta x, which would be b minus a all over n. Well, in this case, it's 1 minus 0 all over n, which is 1 over n. Okay, so that's my width of every single rectangle. Step 3, let's think about this interval and what it would look like. Well, it would start off, sorry, let me use black. It would start off at 0, and it would go to 1, and we would have to break this into in pieces, right? So here we're breaking it into, and then in all honesty, I don't know how big these pieces are, so I'm just going to put a dot, 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 meaning continue the pattern, and then it would go to 1, right? So we're going to break it into all of these pieces, in pieces, however many that is. But what I want you to think about is, what would we be labeling these pieces? So you always start with 0, and then you add the width of every single one of these to each one of the pieces, right? So from 0, it would be 0 to 1 over n, and then the next 1 over n. Plus 1 over n would be 2 over n. Plus 1 over n would be 3 over n. And in general, what would it be? What would that, let me go ahead and draw like a random one for you. Give me a second. Let me think about a random interval here, because then you end on 1, right? So on a random interval here, it starts off with 0, so it looks like it would be what? I minus 1 over n, and then I over n. It's just some number, whatever your counter is. It started off with that number minus 1, and then to the right of it. So like my first rectangle, the left endpoint is 0 over n, and the right endpoint is 1 over n. So for the first rectangle, it's 1 less to the left and 1 more to the right. So it'd be I minus 1 and then I over n. Now I get to choose any one of those values that I want for any interval. So for any interval, I could choose I minus 1 over n, I could choose I over n, or any place in between them. Well, what's the nicest looking one of those? I'm going to choose the right endpoint for every single one of those. For every single one of those, I'm going to choose the right endpoint for every single one of those, okay? So what do I need to do now? Now I need to think about, and that was step 4, now I want to think about what's the height. Think about for the rectangle, what's the height of a rectangle? And then what's the H-E-I-G-T-H? Wish I could spell. What's the height of one of these rectangles? And then what's the width of one of these rectangles? Well, the height, we have to plug the function value in, which we said in general was f of I over n. And in general, the width, we said, had to be 1 over n. And then that's for each one of the rectangles, but then we need to sum these rectangles from I equals 1 to n. So once we find that height and we find that width, we have to add them all together. So what would we have here? This would be the sum of I equals 1 to n of the height. Well, my function, we know our function. Our function is x cubed. So wouldn't that be I over n cubed times 1 over n? So isn't this the sum is I equals 1 to n of, well, wouldn't it be I cubed over n to the 4th? Isn't that true? Because you would have n cubed and then it's times 1 over n. But remember here, n is a fixed number. I is the variable. So what can we do with the fixed number multiples? We can pull them out in front. So this is the same thing as 1 over n to the 4th times the sum I equals 1 to n of I cubed. Well, this is bringing it back to where we started off. We started off with having the formulas for the sum of I cubed. So this was given to us on the first or second page of these notes. We know that the sum of the cubes is n squared times n plus 1 quantity squared all over 4. So this is the same thing as 1 over n to the 4th times n squared times n plus 1 squared all over 4. Well, let's do some simplification here. This would be n squared on bottom and just a 1 on top. So I'm getting this entire sum of all the areas is going to be equal to n plus 1 squared all over 4n squared. That's what I'm getting. N plus 1 squared all over 4n squared. We could even separate that out if we cared about it. That would be the same thing as n squared plus n, so plus 2n plus 1 all over 4n squared. So the area, if you use n rectangles, without having to find the sum of, imagine if we used 1,000 rectangles, right? You're not going to add 1,000 of them. We were able to use a general, which endpoint we chose, the general width, and we were able to find the exact area using n rectangles. That's awesome. But now what did we want to do? We wanted to move the number of rectangles to be infinite. So what we need to look at is the limit as n goes to infinity of that answer. So the limit as n goes to infinity of n squared plus 2n plus 1 all over 4n squared. Well, I know that that is balanced. And if it's balanced, I know it converges to the ratio of the leading coefficients. So just take the leading terms, n squared over 4n squared. So that's going to go to 1/4. So what's the entire area beneath the curve of x cubed on the interval from 0 to 1? The exact answer is 1/4. This is crazy stuff here. What we have done is taken the curve, we found the area of n rectangles beneath the curve in general. You didn't actually give me a number. It's not like we found 4 rectangles or 5 rectangles. We found n rectangles. We found the exact area would be no matter what the number n is, and then we took the number as n went to infinity, a limit, and we were able to determine the exact area beneath the curve. So here's the picture of x cubed. Here's the interval 0 to 1. That red shaded area has a value of 1/4. You have officially just found the area of your first non-regular, meaning non-normal shape, most likely in your life, right? Because all you've done now is circles and triangles and rectangles and things like that. You have found the area of a shape, this shape right here, that is nothing like any of those. You found the area of this crazy curved shape. You found the exact area. Really, really cool concept. Okay? Let's give this a try again. Let's look at example 8. It says, find the area of the region bounded by 4 minus x squared, the x-axis, and the vertical lines x equals 1 and x equals 2. So again, we're not using left endpoints, we're not using right endpoints, we're not using midpoints. We're using any point on the interval, and we're using n rectangles. So let's see if we can do it. Okay, first things first, think about how many rectangles do you need. Here we need n rectangles. Again, we're not specifying the number. Step 2, let's think about that width. What's the width of that? Well, the width is always delta x, which is b minus a all over n. Well, in this case, the right endpoint is 2, the left endpoint is 1, and n is the number of rectangles. So that gives us the width of every single one of them is 1 over n. Step 3, let's think about this interval, right? So we have this interval, and then we're going to have an ith one, and then we're going to have the last one, right? So we break this from 1 to 2, and we're going to break it into a whole bunch of intervals. In fact, it's going to be in different intervals, in different rectangles that we need to break it into. So let's think about what it would be for each one of those. We start off 1, and then we always add the width. So it'd be 1 would be the first one. Then the next one would be 1 plus 1 over n, right? The next one would be 1 plus 2 over n. 1 plus 3 over n. Okay, so think about it. On the first interval, it starts with a 1, and then it's 1 plus 1 over n. The second interval, it's 1 over n to the left, 2 over n to the right. So the second rectangle, 1 over n to the left, 2 over n to the right. The third rectangle, 2 over n to the left, 3 over n to the right. So what would the ith rectangle be? It'd be 1 plus whatever that number is minus 1 over n, and then 1 plus that number over n. Okay, so the idea is we have to pick some number between 1 plus I minus 1 over n and 1 plus I over n, and I can pick whatever number I want. Well, the easier of those two seems to be the right endpoint. So for every single one of them, I'm going to choose the right endpoint to determine the height. So now let's think about finding the area. If I want to find the area of the rectangle, what I'm going to do is always do the height times the width. Well, how do I determine the height? The height is I plug that function value into the function. In this case, it's f of 1 plus 1 over n, right? 1 plus, I did that wrong. 1 plus I over n is the general one. And the width we decided was 1 over n. Okay, so that's the area of one rectangle, but if we want to find the total area, we need to find the sum of all n rectangles. So let's do some math here. What's f of 1 plus I over n? Well, we need to plug that into the function. So that would be 4, let me zoom in here. We're going to have some math that we have to do. That's going to be 4 minus whatever function value I plugged in, which was 1 plus I over n, quantity squared. And then all of that's times 1 over n. So now I need to do some simplification of this. So this would be 4 minus, 1 squared, 1 times 1 is 1. And then we would have a plus I over n, so it would be plus 2I over n. And then it would be I over n times I over n, which would be I squared over n squared. And all of this is times 1 over n. I'm going to do some more math here. What can I do? I'm going to subtract each one of those terms and then let's do 4 minus 1 would be a 3, right? And then we would have distributing the negative minus 2I over n and then a minus I squared over n squared, right? All of this is times 1 over n. So this would be, I need my sigma on all of these, but I'll do that in just a second. So this would be 3 over n minus 2I over n squared minus I squared over n cubed is what I'm looking at here. Okay. And then on each one of these, I still need the sum from I equals 1 to n. The sum from I equals 1 to n. The sum from, wow, that looks horrible. Give me a second. The sum from I equals 1 to n. And the sum from I equals 1 to n of each one of these terms. Okay, so what can I do now? Now I can substitute in every single one of these values. For instance, what's the sum of, well, let me separate them. Maybe it'll help if I separate them. This is the same thing as, remember I can plug in, well, here I can actually pull out the 3 over n. So it'd be 3 over n times the sum from I equals 1 to n of just the number 1. And then it would be minus 2 over n squared. Remember, n is a constant here. Times the sum from I equals 1 to n of I. Minus 1 over n cubed times the sum from I equals 1 to n of I squared. Okay, so that's separating it. Now I need to go back to that first page and use all of the different formulas that I had for each one of these. So for instance, what's the sum from I equals 1 to n of the number 1? Well, that was just n, right? And then we have the sum of I. The sum of I, according to the formula, is n times n plus 1 all over 2. And then the sum of I squared, according to the formula, is n times n plus 1 times 2n plus 1 all over 6. So that's what each one of those turns into. So let's continue doing some math. So this would be 3 over n times n minus 2 over n squared times n plus 1 all over 2. That's a 2 right there. That number's a 2. And then the next one is minus 1 over n cubed times what we got, which was n times n plus 1 times 2n plus 1 all over 6. Okay, let's do some simplifying. The n's simplify in the first one. N squared and n would simplify in this one to a 1 and an n. The 2's would also simplify, actually. And the next one, the n cubed and the n would simplify into a 1 and an n squared. And let's see if we can clean this up. So I'm getting 3 minus, looks like I have n plus 1 all over n. And on the next one, it looks like I have a n plus 1 times 2n plus 1 all over 6 n squared. Okay. So I can go further and try to separate and simplify each one of these terms. So this would be 3 minus n over n is a 1, and then plus 1 over n. And then on the next one, well, I'd have to distribute this out. So let's think about what this would be. This would be 2n squared, and then you'd have plus n plus 2n, so that would be plus 3n, and then you'd have plus 1, and all over that's over 6n squared. So if I simplify each one of those terms, 2n squared over 6n squared would be 1/3. 1/3. And then 3n over 6n squared would be plus, would that be 1 over n? And then we'd have plus 1 over 6n squared. So there's each one of those terms right there, right? So then I'd have, 3 minus 1 over n minus 1/3 plus, or sorry, no, minus, I have to distribute my negative, right? Minus 1 over n minus 1 over 6n squared. Combining like terms, so let's do 3 minus 1 minus 1/3 is 5/3. And then we have minus 1 over n, so that would be minus 2 over n. And then we have the minus 1 over 6n squared. So that's what I'm getting when I have in rectangles. So the area, if I had in rectangles, I know this is a mess, guys, but that's what it is. The area, if I had in rectangles, you tell me in rectangles, this is what the area is going to be. Now this is, I specifically chose using the right endpoint. Again, because we have so many rectangles, it doesn't matter if you use the right, the left, the center, or what point you use, but I specifically chose the right endpoint to make the math easier. Yes, that was easier math, believe it or not. So that's for the area of in rectangles. But what did we want? We wanted that number of rectangles to approach infinity. So if you think about the limit as n goes to infinity of 5/3 minus 2 over n minus 1 over 6n squared, what happens with that? Well, the limit of a constant is the constant, so that'd be 5/3. 2 over n's going to approach infinity, so the bottom gets bigger, which means the overall thing approaches 0. And 6 over n squared, again, the bottom gets huge, so the overall thing approaches 0. So what's the limit as n goes to infinity? It's 5/3. So we just found the exact area beneath the curve of 4 minus x squared, the x-axis, the vertical lines, x equals 1 and 2. How did we do it? We used an infinite number of rectangles and the fact that we know limits, which we did in the first chapter of this entire class. So nice way to bring it all back together. Again, doesn't look like we used too much calculus in this class. The only calculus we really used was the limits in the last step. Every single other thing here was just straight up algebra. Again, this is the only calculus that we actually used on this problem. So hopefully that makes sense to you.